This is a recorded lecture for standards and research trends in wireless communications, primarily wireless. And we'll start off by talking about standards, the standards process, and some common standards organizations. We'll touch on a few advocacy organizations also, which are kind of related to standards. They do help promote standards and push them through and advocate for certain things to be included into standards. And then we will conclude looking at some research trends. All right, so it's super important in communication systems to have some sort of standardization process because we want compatibility, right? It's your radio's not going to be any good if you can't communicate with other radios, transceivers, that type of thing, right? So when we're communicating, we're trying to move information from one location to another, and we need some sort of standardization process to ensure that each radio in that network, maybe it's two, maybe it's a whole lot more, know the modulation levels and depths and the frequencies that you are expecting to operate over, and all sorts of other operating parameters. Right, so this promotes compatibility. We tend to focus on the transmitter and the waveform so that what is actually transmitted and is out there in the channel is very well defined. Then, as a company organization, you can kind of focus your creative, innovative energies on trying to build the best receivers possible. And but you know what the waveform looks like, and so you know how to receive that, or you can add techniques that maybe your competitor doesn't have, and that type of thing to distinguish your solution. So we standardize the transmitter process and the waveform. There's still room to innovate on the transmitter. You can implement things in better ways, but it's ultimately the transmitted waveform that gets specified. Typically, there's a very diverse set of participants involved in the standardization process, and these are mostly global type organizations because we have a globalized economy, right? So it can take several years to from the initial concept of a new type of communication system, or maybe just a new revision on an existing type of communication systems, like going from 5G to 6G or something like that. It can take several years from that initial concept to actually having a standard that's approved by all the different constituents, and you can make and manufacture and market equipment according to that standard. The process involves proposals, and you might run a bunch of simulations. Patent pools can be a big part of the overall standardization process. If you've got a research group and you come up with some whiz bang new way of doing communications and you patent it, then you want your the standard to be written around your patent, because then you get royalties out of everything that's sold according to that standard. And the different constituents have different patents, and they the ones that get written into the specifications, the standards, then those participate in the patent pool. So when a system is sold, a radio is sold, then there's some portion of that that goes into this patent pool, and it gets divvied up to the patent holders. That's very crude description of it, but patent pools tend to be a big part of the evolution of these standards, from proposal through to negotiating between all these diverse participants, what technologies actually get adopted into that standard. Some examples are 3GPP. That's the organization that standardizes our cell phone, mobile communications type technologies these days. Think LTE, 4G, 5G, and coming 6G. IEEE is a big standards organization. Maybe you're a member, probably a student member. I've been a IEEE member since my college days. And Bluetooth, another example. There's a whole bunch more. Bluetooth is kind of a separate standards organization because it was originally controlled by, I think, Ericsson. I should have known. I should have looked that up. So anyway, there's a specific standard for that. A very common one, which you are probably familiar with, is the IEEE 802 series. And the one that we're likely most familiar with is the 802.11, which is our wireless local area networks. And when you're sitting in a classroom and you're maybe using your laptop or your phone, you are likely connected to the campus Wi-Fi network, right? So that good part of that standard is, or operations of that Wi-Fi type of thing is standardized in 802.11. We also have 802.15 for wireless personal area networks, and 802.16 is broadband wireless metro area networks. So much larger. So this would kind of be like the mama bear. This would be the papa, the baby bear, and this would be the papa bear, right? So wireless metro areas would cover a whole area. Then there's a few more unique ones: TV white space, coexistence methods, wireless regional networks. You can get all of these by clicking on this link. It's not always that IEEE standards or other standards are available for free. Sometimes and oftentimes you have to pay for them. But the IEEE GET program is underwritten by sponsors, and so that is free. And some of these standards don't get wide adoption, and they end up being retired and that type of thing. So these things can vary, and there's more. And of course, 802.11 keeps getting upgraded and updated, and we tack on little letters after this to reflect which version you're dealing with. So the IEEE Standards Association has a very specific and highly documented process to develop a standard, and this is to ensure that things are done in a fair manner. IEEE is an international organization, and there's lots of different constituents that are involved in creating a standard, and we want to make sure that it's done properly. Occasionally, there's some mischievous behavior goes on in these standards, and the kind of overall standards organization, the standards board, steps in and may shut down a standards process. So it starts with initiating the project. You would create a project authorization request, and really anyone can do this. Then you need a sponsoring standards committee to kind of sponsor then a study group that would look at this. So then you can move on to mobilizing the working group. Now this is an open process. It's not a closed process. People can join, in other words, and it's governed by this IEEE Standards Association Standards Board bylaws, operational manual, and standards committees and working groups policies and procedures. and the agendas and the minutes of these different meetings of the working group are published. Then a standard is drafted, and this may take quite a long time to do. And a lot of projects that are started don't get to this state of drafting the standard. But once the standard is drafted and it's gone through this working group, and everyone in that working group is relatively happy with it, then it can be balloted. And balloting here is a little different from the voting type of situations you might be more familiar with. It seeks consensus across a diverse set of interest categories. It might be manufacturers, it might be these advocacy organizations, it might be regulatory agencies, maybe. And, just looking at getting lots of different people or stakeholders involved, so you get a diverse set of this interest categories. So it's not just jammed through by some big corporation or something like that, right? And so the threshold ends up being that 75% of the ballots are returned with 75% approval, and that's pretty high threshold to reach, right? But so there's a lot of work done up front to make sure that once you start balloting, you're going to have people that are motivated to actually fill out the ballot, return it, and hopefully vote for approval. All comments are addressed. It's typically open for 30 to 60 days, open to the balloting group, and which is going to be typically much larger than the working group, right? And it's open to review and appeal. So this is, just a much squishier process than we think of in, let's say, our political elections or whatnot. Then to gain final approval, the IEEE Standards Association Standards Board approves it upon recommendation of the Standards Review Committee. And it's mostly focused at this point, at this level, it's mostly focused on whether procedures and guiding principles were followed. All the things here in this bylaws, operation manuals, and all these policies and procedures, right? So the working group can come up with technology and mash it together in a way that they think is right. But you've got to make sure that when you go out to balloting, that you put together a balloting group that is a diverse set of these interest categories, and that you ultimately get consensus. Now, once the standard has been approved, then you kind of shift into a maintenance mode, and there's then now various revisions done to that, and to enhance it, to maybe fix something that thought was going to work but didn't end up working in practice, and that type of thing. All right, so in addition to these standards organizations, there's advocacy organizations, and these are organizations that will essentially lobby on behalf of their members, right? So CTIA is a big one, and but then there's some much more specialized ones: Wireless Innovation Forum, Dynamic Spectrum Alliance, and the Alliance for Telecommunications Industry Solutions. So these are the ones that I'm kind of personally familiar with, have been involved with in the past, and that type of thing. So lots more, but these are just some of the big ones. So let's take a look at a few of these. Let's see if I can okay, so here is the 3GPP website, and I've drilled down into a section where we're looking at different standards. The overall, let's say, 5G cellular system is composed of many, many, many different standards. Some of these standards are short and to the point, but there's a lots of them. And here's just the ones that are involved in. Let's see, what is this? Well, maybe I'm sorry, here it is. The radio technology beyond LTE, right? So there's 221 specifications. Here's just the first page of, it looks like 5 pages or something like that of these things. And so here's some example ones. I showed you kind of an older uh, version of this. Actually, is this an older version? I think it is. Yeah, this is release 12. So this is the one I was showing on Friday's in-class lecture. Let me pull up some of these others. And, well, I thought I had them up already. I think... So they're in Word in these versions. So here's a standard. So it's a technical standard 38.201 version 15.00, and it was approved on 2017 December. So it covers the radio access network, the new radio, and more specifically the physical layer and the general description of it, right? And so you go in here, it's got some basic title page type things, copyright notification. You've got table of contents, a forward here, and a description of the versioning process. You see, it's very, very rigorous. If you haven't, maybe you've worked in a summer internship and you might have been exposed to some documentation, engineering level documentation, but things get very, very specific. It's a little bit verbose, but once you get used to it, you know where to look for the information. So there's a general scope. It's kind of like an introduction. It's saying what the present document is describing, and in this case, it's giving a general description of the physical layer of the new radio interface, and particularly it's describing the other documents that go into this overall series, the 38200 series. And so it's referencing these other documents. It's got a section where we have some definitions, some abbreviations, and here you start to get into this general description of layer 1. So here that's showing the overall architecture. You've got the physical layer, and that's mostly what we've been studying in this class, right, to this point. And then you have medium access control and some connections between these, right? And the data flow is going in this direction, and then you've got a line out here that's showing that you've got a control line and measurements, right? So remember how we talked about in an OFDM, each subcarrier can be modulated to a depth that's consistent with the measured signal noise ratio, right? So here, this radio resource control block, it's up here at layer 3, so it's operating at a higher abstraction than the physical layer, but it's telling the physical layer, make some measurements of the signal noise ratio and all the different subcarriers, and report that to me, and it will then send back control, do those calculations, send back the control information to the physical layer that will say exactly how to modulate each subcarrier group. Then we've got a little description. In this case, we're the lowest layer and the physical layer, so it's talking about some services that are provided to the higher layers. And then it talks about these are different kind of virtual channels. So different parts of that resource uh, grid will be devoted to different control channels, right? Where if I need to communicate some non data but control type information to the user equipment, subscriber units, that type of thing, the remote radios, then I'm going to use some of these control channels, right? So, or if I'm broadcasting to all the different users, I'm going to use this a physical broadcast channel, right? And so uh, talks about the coding scheme for transport blocks is a quasi-cyclic, low-density probability code sweat. I just said that this morning or this afternoon. Now I'm blanking on exactly what that stands for, but that's the type of codes that we're using in these systems, right? So it's not giving you a lot of information. This is again just a high level view of it, and talks about that there's functions that are provided in this physical layer that are cell search. How does a radio actually find a cell station to communicate with? How is power controlled? Does radio operate at full power all the time? No, that would be wasteful of batteries, right? So we can control all this. There's synchronization and timing, and this HARC is the hybrid automatic request. So if you've your packet, you've determined that there's a bit error in that packet, then and you can't correct it, right? You've had too many errors, so many errors that you can't correct it using these forward error control provided by these LDPC codes, then you would basically ask for a retransmission, right? And we talked a little bit today about some beamforming and channel state information we talked about a lecture or so ago. So then here's some measurements and whatnot. It's a little bit more of a description. And here what we're doing is this is kind of the parent standard for all this whole series, this 38200 series. In particular, this is a 201, right? But it's showing how these other standards within the family all relate to it, right? And so it's telling you where to go find it. And then you can come back over here and say, all right, well, I'm actually pretty interested in the let's see, this physical channels and modulation. So I'd come over here and I'd find 211 and I click on this, and yeah, you got to jump through some hoops to find it, but eventually you do. And let me drag this one over to this slide here. And so now here is a more detailed one. This is the physical channels and modulation, right? So this is the 211 that is referred to by this standard right there. And so now here's where we get real, and we start looking at the downlink frames and the uplink frames, and it starts giving you these different specific things here. 10 millisecond duration for the frame. A subframe is 1 millisecond in duration, and each frame is divided into two equally sized half frames of 5 subframes each, with half frame 0 consisting of subframe 0 to 4. Oh, wow, right? So very, very, very specific. Here's some more examples. There's some transmission times between when you receive a frame and then when you turn around and start transmitting it again, assuming that you're in a time division duplexing type situation. We've used this term here, these slots, and you can see that it's these things are defined here. on how they're numbered. I think I mentioned some things about this resource grid. And so we have this resource grid of these number of subcarriers and OFDM symbols and so on. Let's see what's interesting here. So here we've got these values in a range 0 to 3299 represent the number of the DC subcarriers, the value. Okay, so very, very specific type information. Here's another number. We mentioned that a resource block is 12 consecutive subcarriers in a frequency domain, right? So that we are using this resource block to say, all right, so we're going to modulate all the subcarriers in that resource block in the same level of M-ARI Comm. Right? And so just giving you a flavor for how these things are done. I think if we go down here a little bit farther, we start to see the modulation, right? So we talked a little bit about gray coding and that type of thing, and how actually these constellations are built up. And so here's the different constellations that are supported, and it gives you the constellation locations mapped out, and all the way up to 1024 Quang, right? And we talked about some sequences, some special purpose sequences that are used. So this is telling you how to generate a link 31 gold sequence and some other things. And so if you're writing software firmware to actually implement one of these radios, then you bury yourself in the standard and you pick out all these numbers, and this is how you encode all that information in your waveform. All right, so talk all night on this. Yeehaw. Okay, so let's look at some organizations here. So let's start with CTIA. So CTIA represents the U.S. wireless communications industry. This is mostly your carriers and for cell phones and that whole ecosystem, right? So they hold a huge conference every year, and cable financial news networks like CNBC and Go, and they do remotes from this. So it's a really big deal, and but it's an advocacy organization, right? And then we have this Wireless Innovation Forum, and this is really kind of promoting more of kind of the research ideas and trying to advance technology and getting it introduced into actual systems. Dynamic Spectrum Alliance is another organization that is promoting the idea that we can gain efficiencies out of our systems by allowing spectrum to be dynamically allocated instead of kind of like allocated once and forever by the FCC through an auction process. Maybe that's a primary user, but then secondary users could be much more dynamic and use spectrum that's out there as long as you don't interfere with anyone else, right? So we'll talk a little bit about that in the machine learning lecture on Tuesday. So and then there's ATIS. This is kind of the U.S. Organization that works with 3GPP and other type systems, again advocating for its members. All right, so all right, let's go back to our slide deck, and now let's talk a little bit about research trends. So 5G's been around for several years now in the marketplace, and of course before that in the standards process and a research process. So right now, the focus is on release 18 through 20. And so we've got activities going on at both in each of release 18, 19, and 20, right? So 17 is the one you could say that is actually out there in operation, right? If that makes sense. And 18 is kind of a shorter term thing. It's moving quite along. 20 is still kind of out there, right? But while we're working on these things, and some of the focus, I've just picked out a few things. There's lots of different things that are being focused on here, but it's basically advancing 5G. The 5G that's out there right now is mostly the one that us as consumers are familiar with, that enhanced mobile broadband use case, the EMBB, right? And but a lot of those other use cases are still kind of being developed in this advanced process, right? So they were conceived of and started to be defined, but now we're kind of drilling down on them and really enhancing them. So a lot of work being done in MIMO, non-terrestrial networks, basically meaning that we're communicating with our cell phones with low Earth orbit satellites. You're probably familiar with Starlink and other type of systems out there is OneWeb, and then Project Kuiper from Amazon, all trying to operate these low Earth orbit satellites. And there's a lot of work on trying to integrate our cell phone technology, right? 5G cell phones with these low Earth orbit satellites. And a ton of work on AI and ML, and that's again a separate lecture we'll talk about. So, for example, actually in a couple of weeks, and May 8th through 10th, there's going to be a workshop on 6G, and they're going to be defining the use cases, right? So we've already been talking about 6G for a while now, and I've watched a number of webinars on it over the past year. And but now people are meeting in the Netherlands in a couple of weeks for 3 days to really define these use cases, and just some of the things, immersive Internet of Things. These are going to be big deals. So some other research trends, which are kind of, if you look at some of these more advanced things in 5G advanced and 6G, you'll see some of these things, right? So I'm actually going to be a little bit repetitive here, but there's this ambient backscatter concept, especially useful for IoT. The military is interested in this, defense organizations are also, but it's basically like you could have a smart surface, maybe something that's placed on a wall of your office or building, and you can manipulate that surface, right? And then you can control reflections off of the signals off of these surfaces. And you could also do maybe some beam forming and that type of thing. So the idea now is that you could have a transmitter, but then separate from that, you can have this thing that's creating a scatter of that. And if you do things right, you can either do your communications in that way, or modify that communications in one way or another. So we mentioned today about the millimeter wave and the challenges there, and so there's a lot of work being done in implementation of the theory at millimeter waves, and particularly this beam forming. This is at non-terrestrial networks, integrating with LEO, low Earth orbit satellite constellation. Low Earth orbits, think of it as like 200 miles up or so. So, as opposed to geosynchronous satellites, which are several tens of thousands of miles up. And also, like GPS satellites are in medium Earth orbit, and there are a few 10,000 miles up. And then dynamic spectrum access, which I've touched on and we'll look at more. All right, so what about the DoD? So these are mostly commercial type things, and but the DoD does a lot of research, and I've worked in the DoD, and so that's kind of where I focus a lot. So there's a few things here. The Army's Project Linchpin. This is AI and machine learning applied to electronic warfare, signals analysis. Really, it's kind of morphed into more of doing machine learning at the far edge and doing that securely and robustly and reliably. But the big application of that is in trying to add this to electronic warfare. And electronic warfare is all about detecting an adversary's signals, jamming them, using them to maybe target, and then also responding or overcoming jamming and trying to still communicate in a what we call a denied environment or contested and denied environment. So DARPA's has this RF MLS, so radio frequency machine learning systems. They've also have a space-based adaptive communication node. Again, trying to uh, uh, bringing flexibility to LEO satellite constellation crosslinks. When you have a satellite in low Earth orbit, it is low enough that it doesn't see the whole Earth at once, right? And so, if you're trying to communicate with the ground station, you're going to pass that ground station in about 10 minutes, and the rest of your orbit, you can't communicate with that ground station. That might be 90 minutes before you come around, and by then the Earth's rotated, and now you've got to find another ground station. Maybe there's only these maybe 10-minute communication windows a few times a day. So if you're just working with one low Earth orbit satellite, you can't hardly communicate like that, right? And so a whole constellation is built up of many satellites, and then they not only is the satellite communicating with a user on the ground, but then it's communicating via crosslinks with other satellites and to kind of hop over in a network, mesh network type of configuration to a satellite that actually is passing over a ground station and can downlink the information there. And so these need to be pretty broadband type communication networks. DARPA also has this generating communication channels to operate using 5G network slices. So if you go a few layers up in 5G in that network stack, we're well above the physical layer now, but the 5G system is designed to have these network slices so that you could have one physical system but run several different networks over that, and the networks would be isolated from each other in that way. And so the idea would be that we can, how do you use commercial 5G systems to create some secure links and secure networks that operate over that and still can coexist with the existing system. IARPA is the Intelligence Advanced Research Projects Agency, so think of your intelligence agencies and stuff. So a little bit different from the Defense Advanced Research Projects Agency. Here they have the Scissors programs securing compartmented information with smart radio systems, detecting vulnerabilities by looking for anomalous transmission. So there's a lot of different things going on here in these really kind of advanced type of projects. There's usually a number of different thrust involved in each one of these over time. And these are usually multi-year type research programs. Um, Secure position, navigation, timing is not exactly communication, but we're communicating, like in a GPS type system, your signals such that you can determine your position, you can navigate according to it, and you get precise timing because GPS systems, overall GNSS systems, are based upon atomic clocks, so you get great timing, and that timing is what's used to figure out your position. Well, all these systems are routinely jammed or spoofed in conflict areas, and so it's a real problem. So there's a lot of efforts aimed at securing this approach, including using some AI machine learning to try to detect jammers or trying to detect whether a particular signal is spoofed or not. So then actually high frequency communications goes way back. Think the communications that were used in World War II and also this would be in maybe the let's say 7 megahertz region, right? Instead of what we're used to dealing with nowadays is in the hundreds of megahertz and gigahertz is where a lot of our communications, our cell phones, and our Wi-Fi's are operating at, right? But the high frequency communication allows us to communicate, hundreds and thousands of miles, but primarily because the signal can reflect off the ionosphere and bounce around the globe. But it's very, very dependent upon propagation conditions. So there's this effort to predict that. We've gotten used to satellite communications and that type of thing. It's easy to have satellite or fiber optic, transatlantic, transpacific, transoceanic type cables, right? And we can communicate anywhere around the world. But these systems are vulnerable in a defense-oriented conflict type situation. Cables are cut. I think I saw a headline today that there was a cut of a fiber optic cable off of Africa, and so some of the islands, I didn't actually read the article, but I assume it's something like the Canaries or something that's off of Africa, off the west coast of Africa, and that they have lost their internet connection that relied upon that fiber optic. And I assume that was an accidental cut, but in a conflict that can be cut. Some of our near peer adversaries have an ability to take out satellites in orbit now, and so we are looking into these high frequency communication systems to be able to communicate with our assets around the world. And all right, so here's some current DoD SBIR, Small Business Innovative Research grants. So if you're a small business, I think smaller than 500 employees, there's some other criteria. You got to be U.S. Owned and controlled. And there's also the Small Business Technology Transfer research grants. And these are where a small business would work with a research institution like a university or some other research-oriented lab, and kind of collaborate and transfer technology from the research domain into practice, right? And so there's lots of other things. It's just so happened that these were released a couple of days ago, so this is about as fresh as you can get. I'm recording this on Friday, what is it, April 26, 2024. So the Army has a topic on underlay communications with wide signal to interference and noise ratio range. And basically it's aim to use cognitive radio. So you're building in some AI or some machine learning into this radio, and spread spectrum, which we've talked about, to communicate covertly in an interference environment while not assuming the interference is noise-like, right? And so here they're trying to use spread spectrum and spread out that signal so it's not as easily detected, and that it can operate on the same frequencies that other stations are operating on, and that's why it's now the signal, once it's spread, is the energy is the same, but the power spectral density is lower because you spread that energy out in a wider frequency range, right? And so that's why we call it underlay, because it's kind of sneaking under the cover there, right? And the interference environment. So again, some of our more simple approaches will assume the interference is noise-like, so we can use the Gaussian, central limit theorem and Gaussian tools that we have. But that's not always the case, right? And so you want to be able to leverage that information and do that very dynamically. The Air Force has detection and geolocation of signals of interest given distributed end user devices. So this is basically, so soldiers are provided some military grade cell phones, and just like our regular cell phones, they've got lots of sensors on them, and we can use these to detect and localize different signals of interest, right? So the classic one, one of the more important ones is GPS jammers and spoofers, right? And then etc. With both client side and server side algorithms. So we would, if you would propose to do some research according to this topic, then you would develop algorithms that run both on the cell phone, but then ship that information to a server, and maybe that server would gather data from multiple different of these cell phones in an area, and then crunch it to try to identify and localize these guys. The Navy has several that I found relevant and interesting. They have this wireless integrated network, high capacity, low probability of detection, right? So we talked a little bit about low probability of detection and anti-jam in the spread spectrum lecture. But basically, you're trying to do covert comms and encode these waveforms in FPGAs so that they can be implemented in high bandwidth, high capacity type situations, and maybe swapped in and out. They also have scalable wideband multifunction radio frequency payloads, and so this modular open systems approach, or sometimes called architecture out here, MOSA. This is the thing that the defense industry is trying to promote to try to get away from proprietary solutions from one defense contractor trying to build in their proprietary stuff, so that they've got to keep going back to that contractor, right? So they're trying to force these defense companies to build things in a more modular and open way, so that they can kind of unplug one module and plug in a different module, even down to the software level, right? And so have that approach for waveforms for UASs, unmanned type drones and various type of platforms. So the Navy obviously works in both air, surface, and under the water type of situations, and they even work on land too. So a lot of different type of autonomous systems, unmanned autonomous systems. Then also finally, the Navy has the signal queuing in complex environments. Here they're dynamically retraining machine learning algorithms to detect and characterize signals from a very wideband data stream. This well, here let's actually go and look at these, right? So um, let me scroll down here. So oh, I missed that one. Maybe we'll go back to that one. Oh, I missed that one too. Okay. So this one, this technical point of contact, or the topic point of contact, TPOC. This Deborah Van Vechten has worked. She's with Office of Naval Research down in the D.C. area, metro area, and she's worked with a company I know of in Elmsford, New York, near White Plains, and they build superconducting electronics operating at 4 degrees Kelvin with zero resistance. That's why we call it superconducting, and they can digitize very wide bandwidth, very high speed waveforms. So I'm thinking that that's related because she's worked with them before. It's just kind of background information, but you can look at here, and here it's all these kind of form this same little a pattern. You've got an objective and then a description, and looking at doing CPU, FPGA, GPU, systems, and that type of thing. I actually worked with this Deborah Van Vechten on a GPU CUDA-based demodulation of waveforms, but it's this wideband data stream. So you look through these things and try to pick out what they're really looking for, and then respond to that. So let's look at some of these others that I didn't get into that PowerPoint slide. Radio frequency real-time modeling and simulation. So design, develop, and incorporate realistic environmental responses to radar signals from VHF to X-band, including free space propagation, terrain, and ocean scattering, multipath signals, and ship targets. So this is more radar, but again, radar is very, very related and relevant to the many of the topics we've talked about in this course, particularly spread spectrum and that type of thing. So. And then small satellite swarms for ISR. ISR is intelligence, surveillance, and reconnaissance. So, and so you're basically systems to monitor an area. So develop methods that are capable of using swarm-based architectures in the orbital domain for performing both Earth observation and space domain awareness tasks for support to multi-domain operation. Multi-domain operations means that our Navy and Air Force and Army or Marines, Coast Guard even are all trying to work together. That's still aspirational. They don't always work together, but we talk about it, right? So all right, so lots of different things. So you can see as I scroll through here, there's lots of different research topics. These are just the ones that I found that were particularly relevant to the course we're talking about. Here's some other articles that I found just by going to the wireless communications transactions, or is this from letters? But actually, I think it's maybe the magazine. Secure wireless communication via intelligent reflecting surface. So I touched on this earlier, and so here's a paper talking about that. With the advancement in microelectromechanical systems, MEMS, and metamaterial techniques, it becomes feasible to control the phase shift of reflected signals in real time via a programmable surface. This has enabled a new wireless device named Intelligent Reflecting Surface which can be flexibly deployed in wireless networks to improve their performance in various ways. So, there's one, here's another one: non coherent massive MIMO OFDM downlink based on differential modulation. All right, I'm not going to go into that one, but uh, again, just some samples of some of the research that's going on. I'm a member of the IEEE Futures networks, and so they run all sorts of different webinars and meetings and that type of thing that really are pushing kind of the future of networks, wireless networks. And let's see, is there anything else I want to show? Actually, I'm going to finish kind of early here, I think. Okay, so I think that covers most of what I wanted to talk about. Oh, here's a little thing. Let's cover these. Here's DARPA, the Defense Advanced Research Projects Agency. Here's the RFMLS, and you can see some of the different areas that they are working on. Now, this is an ongoing program. It's already been competed, but there are groups that are under contract with DARPA, being paid to do research in these areas. RF fingerprinting. Traditional wireless security relies on a software identity for each device, which can often be hacked or otherwise cloned. The RF MLS system will aim to learn to recognize a specific, like an individual transmitter. This could be an individual phone that is different from your phone that you have, even if it's the same model. Because when we try to build RF components, there's a lot of variability in it. It's unfortunate. We try to build things so they're exactly the same, but it's sometimes really hard. And so there's some hardware imperfections within that transmitter. And so that means that each device kind of ends up with its own little fingerprint, right? So that it's unique and can be identified. So power amplifiers are a particular area of this that they have some different characteristics from one transistor to another as they're manufactured, and so they can have slightly different non-linearities associated with them. Spectrum awareness, autonomous RF system configuration, this RF fingerprint enhancement. So some of the topics that are being developed under that research project. Here's this scissors, whatever, I don't know how they pronounce it, but looks like skizzers to me. But this program seeks to develop smart radio techniques to automatically detect and characterize RF anomalies that may indicate a compromise of secure data in complex RF environments. Right? So the specific types of anomalies include low probability of intercept signals, altered or mimicked signals, or maybe spoofed is the word I've used for these GPS signals, or abnormal unintended emissions. So basically, we want to be able to communicate securely. Maybe it's an embassy trying to communicate, or it could be the NSA operating a surveillance system somewhere, and we want to make sure that all that work being done by IARPA is secure, right? And so that there's not other radios trying to either mess with that process or to actually kind of steal signals. All right, and then here's this Army linchpin developing an AI ML operations pipeline. ML ops is what you might see in the industry, and it's called Project Linchpin. And so this was it's kind of started back in January of 2023, And so this is kind of a August update, end of August update on this when it was actually getting going here. So deliver trusted AI ML capabilities to Program Executive Office, PEO. That's kind of a very high level. It tends to be headed by some general or admiral, and it's kind of responsible for overall development of a particular system, right? And this is the IEWNS, right? So let's see, what do they say what that stands for? But it's basically a electronic warfare type system. So it's using AI ML capabilities to process, exploit, and disseminate intelligence data in the volume and veracity collected. And so I was just giving you some timelines, but basically trying to leverage AI and ML. This is a classic Department of Defense slide here where they try to cram everything into there, but it's signals analysis and exploitation basically. So all right, let me see if there's anything else. I think is that my last slide? Yeah, that was my last slide. So it's an hour, so hopefully I didn't bore you too much and drone on for another 15 minutes like I would in class.